Okay, so now we're going to do the harder part of equilibrium. We're going to talk about what happens when you have it in initial conditions. So you're not talking about the values at equilibrium, which is pretty much plug and chug kind of calculations. We're talking about a situation where you're given the initial conditions and you have to do a little bit of algebra to figure it out. So you'll be given the starting concentrations and one equilibrium concentration, not all of them, but you can interpret from there, you can imply from there which way the equilibrium shifted since they give you one value of the concentrations. You're going to use stoichiometry to figure out the other concentrations and KEQ. And what we're going to do is we're going to create a table called an ICE table, and it stands for initial, change, and equilibrium. ICE tables are something I do a lot in AP chemistry. We won't do so much here with them. So see if you can follow along as I go through this. You have some reaction. Here it is. All gases. You have 2 moles of SO2, 1.5 of oxygen, 3 moles of SO3 placed in an empty 1 liter container. At equilibrium, 3.5 moles of SO3 were found to be present. Calculate KEQ. So we're going to set up the initial, change, and equilibrium table, the ICE table. We're going to start with the initial molarity. Well, SO2 is 2 moles in 1 liter, so 2 molarity. The oxygen starts at 1.5 in the 1 liter container. Let me erase that. Then I want you to put a big line down where that arrow is, because we're going to distinguish reactants from products. 3 moles of SO3 in the 1 liter container. So molarity is moles over liters. And now we're going to figure out the change. Okay, it says at equilibrium, 3.5 moles of SO3 were found to be present. So that's equilibrium for found to be present. So now what we can do is we can look at the SO3 and see how did the SO3 change? Well, it gained 0.5 molarity. That tells me that the equilibrium must have shifted to the right because it produced the SO3, which means this side gained, this side is going to lose. So I'm going to put minus signs here. And I'm going to use stoichiometry to help me figure out how much they lost. So if I do 0.5 molarity, which is the SO3, and it took 2 SO3s to be made from 1 oxygen, that means the oxygen did 0.25 molarity. And if I did the same thing with the 0.5 molarity SO3, and it takes 2 SO3s to be produced from 2 SO2s, that means I lost 0.5 on the SO2s. So at equilibrium, here's how it works. I plus C equals E. Initial plus change equals equilibrium. Initial plus negative 0.25, 1.25 molarity. Initial plus negative 0.5, 1.50 molarity. So now I'm going to erase some of this. And I have filled out my ICE table. I hope that makes sense to you. We're going to calculate KEQ using the expression SO3 squared over SO2 squared and oxygen. And I'm going to use the equilibrium values in the equilibrium constant. So I have 3.5 squared, 1.5 squared, 1.25. Divide that out. And you get 4.36 for your value. Okay, so now we're going to do a different one. We're going to still set it up, put a big line down that arrow. We're starting with 1 mole of SO2 in a 2 liter container, so it starts at 0.5 molarity. Molarity is moles over liters. So the SO2 is 0.50. The oxygen doesn't say anything. Must be 0. Doesn't say anything. SO3 is 1 molarity. So now, because there's a 0, there's no way the reaction can go to the right because I'm missing a reactant. It has to go to the left. And if you read the question, it says when the system reaches equilibrium, you have 0.08 moles of oxygen present. Well, that means I have 0.04 molarity of oxygen. So it must have gained 0.04 molarity. This means this side gained, this side lost, and let's do some stoichiometry to figure that out. 0.04 molarity oxygen. It takes 1 oxygen to make 2 SO2. That means this gained 0.08 molarity. And it takes 0.04 molarity oxygen. It takes 1 oxygen to make 2 SO3, which means this lost 0.08 molarity. I want you to make big note here. This is where I'm doing the stoichiometry. Is I'm doing the stoichiometry based on the change. That's all it's based on. So when I subtract, I get 0.92, 0.58 KEQ. The expression is SO3 squared over SO2 squared times oxygen. I'm going to put in my numbers from the equilibrium values. And multiply it all out. And I get 62.9. Okay, so a couple of things to look for. Change is how you do the stoichiometry, and one side gains and one side loses. What happens if you don't have equilibrium values? Well, you have to figure out which way the reversible reaction is going to shift based on the reaction. If it has a 0 on the product side, it's going to go that direction because I can't use up any products if I don't have any. If I don't have any reactants, it's going to go the other direction. What happens if it isn't a perfect square? And that's an example I teach my AP students, but I'm not going to worry with you guys. What we have to do is, if the KEQ is very small, we can approximate the answers, and I will show you how to do that in this section. If it's larger than 0.01, we might have to do some complicated math. I don't expect my AP students to do it. I don't expect you guys to. So if the KEQ is very small, the reactants are favored very much over the products. The reaction is staying on the left side very much. And therefore, you can pretty much assume whatever the initial molarity of my reactant is, plus or minus X, this is still essentially just whatever the initial value is. You can ignore the X in the equilibrium. So for this one, KQ is very small. And I'm again, put my line here. I have 2 moles of ClO put in an empty 4-liter container. So molarity is moles over liters. So I have 2 over 4 is 0.50 molarity. These both start at 0. Okay, because I didn't say anything for them. Therefore, they are going to gain. And this one is going to lose because they have to go this way. Gains and lost. Okay, but we don't know how much they gain. So we're going to use a variable to represent that. We're going to say they're going to gain X. And the reason why I say X is because they have a coefficient of 1. 1X, 1X. But because this has a coefficient of 2, if I did the math, here's my change. I have XO2. 1 oxygen comes from 2 ClOs. That means it's 2X for the ClOs. So 2X here. So at equilibrium, I have X, X, and 0.5 minus 2X. And so now we're going to use the equilibrium expression to find out what X is. KQ is Cl2 times oxygen over this squared. Okay? And what we're going to do to make the math easier is because the KEQ value is very small, we're going to put in X and X, And then on the bottom, I don't want you to FOIL. No foiling, okay? No combining those terms, multiplying that term. Just what you're going to do is you're going to assume x equals 0 with respect to 0.5, because it is going to be really small. So what that does is it turns it into 0.5 and squares it. So when I do this, and I'm going to cross multiply, I get x squared equals 0.0016. I get x is 0.04 molarity. So this is 0.04, 0.04, and this is essentially 0.42. Doesn't change very much. Okay, so we're not going to worry about it too much.